we are back to chemistry, right? We've kind of been like a little bit of science, molecules, elements, chemistry, physics, earth. Now we're kind of back to chemistry. We've seen that last week with the last module, we're starting even with earth science, tying in everything that we learned before, as we had baby steps through. And so again, we're making it personal. Module 14 is just all about making everything that we've learned personal. That means, how does it actually apply in our life? How does it live it out? Why do we get to live and breathe and be on this wonderful planet that God gave us? Okay? So, a couple of things that we need to know from this chapter. It starts out with organic compounds. Organic's the big hot word now, right? Like, is it organic? So when we're looking at organic, think about that just means basic. It's the very base of everything. So if you can only have organic cookies, or if you need organic flour, it's like nothing else has been added. It's not been modified. It is what it is. You haven't sprayed anything on it. You haven't painted it a different color. You haven't added extra high fructose corn syrup. It is what it's meant to be in its natural state. So the same thing when we go to organic compounds, they're just carbon and hydrogen compounds. So these are the two things that we're starting with. So, we've got hydrogen as our very first step on our periodic table of elements. Carbon is 6, right, I think, on there. And so whenever we have just carbon, just hydrogen, we have an organic compound. And then sometimes they have other things added to them. So when we add oxygen to an organic compound, it now becomes it talks about bio. So we've got biology, like bioorganic compounds, things like that, whenever we've added that oxygen. And I just always remember it, oxygen is what we breathe. We need oxygen for life, and bio means life. And so it's added that oxygen in it. You can also add nitrogen in, okay? So when we have organic compounds and we just have them alone, they are also called a hydrocarbon. So you have lots of vocabulary, and that's why I kind of have it up here. I didn't want to go through your module like page by page because you've already read that, but you had a lot of vocabulary, a lot of things that kind of break up into different pieces. How can we make sense of this big puzzle? How does it all tie together? So organic, we're at the basic structure. When it's just carbon and hydrogen alone, it's a hydrocarbon. Super easy. We've got hydrogen and carbon, so they've just smushed the two words together. Okay, so we also think of hydro. Usually what comes to mind when you hear hydro? Water. Okay, because water is what? Hydrogen and oxygen. Okay, so you're hydrating yourself with water. So the hydro, I think sometimes whenever you see hydrocarbon, you're like, oh, liquid. It's not liquid, it's referring back to that hydrogen that's in there, right? So when we talk about just carbon alone, we know that hydrogen stands alone and it has its one little electron. It's right up there. At the top of our periodic table of elements, it combines with oxygen to make water. So what about carbon? Hydrogen's only in one form, okay? It's just one of it, and so that's just how we have it. When we get with carbon, we have 3 different ways that we can deal with carbon, which makes it easy to think because usually we've got a solid, liquid, and gas. So 3 different structures of things too. So carbon has 3 different structures. Diamonds, they all are just carbon, okay? But it matters how we line it up. So again, just like this class, you're all this one class, but if I lined you up in one line, you would look differently than the way that you're sitting at your table right now. So same thing, when we structure all of our carbons in this little teepee shape where each carbon has 4 other carbons attached. So you've got this triangular shape on all sides with a center carbon. It's a very solid structure. And if we think about it, if I were to push, it's kind of like a tripod. If I push straight down the top, I have 3 feet that are supporting me. So it's a really strong structure. Well, this is like a jack. You turn it over. Now this one's on top, but there's still 3 feet there. So no matter how you turn it, it's a very solid structure, which makes diamonds the hardest. Whenever we were talking about our Mohs scale of 10, right? The hardest solid that we have. Now graphite, our carbon is all lined up and it's super strong where they're connected, but they're just connected in layers. So we've got these really, really strong layers and this other really strong layer, but the bonds between the actual layers aren't very strong. So they get to be sheared off. You know, they're like a Kit Kat bar, you know, where you can peel off the wafer pieces of it, okay? Then fullerenes are arranged like a circle. So we're looking at something that's like a cage. They're also called, in your book it uses sphere for your chapter test. It uses the word cage. So they're arranged in this circular shape where they're connected in a ball shape, okay? So we have our carbon, we have our hydrogen. Then how can they be put together? Well, we know we have some that are in these single bonds, kind of like a jack, some that are in layers, some that are in spheres or cages. And so that kind of relates to, we can have saturated or unsaturated organic compounds, right? So I also put these down here, and this goes back to when we were studying about our endings in chemistry, I think around module 4 or 5. We were learning about anes, enes, and ines for it. So remember, if you line them up alphabetically, A comes before E, comes before Y, right? So if we line them alphabetically, they are also in your numerical order, 1, 2, and 3. Anes have a single bond. Enes have 2 or more bonds. So we're looking at that. Ines have to have 3 bonds. So this is a cheat sheet way to remember. You will have to match these up on your test, okay? So here's your cheat sheet way to remember which ones go in what order. So when they have this single bond, we're looking just at our anes here. They are called alkanes. They are all single bonds, we know, because our A goes with our 1, and we have saturated. If something is saturated, it means it holds as much as it could possibly hold, right? So if you saturate a paper with color, it holds as much color as it can hold. If you are saturated with water, whenever you jump in the pool, you're as wet as you possibly can be, right? So the way that saturated works out, it means it has as many hydrogen atoms as it can possibly hold, okay? They can be lined up either in a straight chain. So if we have carbons set up, we know that there's bonds on all sides, okay? So if I have 3 carbons, I would be able to have 8 hydrogens lined up on it. As long as they are all on a straight line, they're straight chained, saturated organic compounds. If they are branched, if we pull one guy down here, now it's got an arm. It's still the whole group together, but it has an extra branch on it, so that's a branch. If they are arranged in a ring, okay, they are called ring ones. Now, another thing about the rings, and sometimes has your mom ever gone to you and said, smell this, and like done like this with her hand or whatever, or if you're smelling something on the stove, you do like this in a hand. That's a good reminder that our aromatic hydrocarbons are circular. Okay, so whenever like we can smell it, something is aromatic and it gets the scent out into the air, we're usually doing this motion with our hand, and that can remind us that those aromatic hydrocarbons are actually set up in a circle. Okay, so we've got these. We have our unsaturated ones, which means they're either going to be an alkene or an alkyne, right? Because these are 2 or 3, so that means we are looking at unsaturated means double or more. So alkenes have the 2. Aromatic hydrocarbons also have a 2, but the difference is that the structure here is going to be straight or branched, and the structure for our aromatic is going to be that circular form, okay? And then our alkynes have 3 bonds for those, okay? Now, something else that we need to take note of is that acids, and we're going to address this today, acids react chemically, right? If you pour acid on something, it's going to eat it away, right? So when they react chemically with something else, we know that chemical changes produce a color change, a change in temperature, right? Or a precipitate. So that's how our acids tie in for today. Let me pull this up here. Okay, so up here we have butane. Okay, I've written these. Let me jump to fossil fuels first and then we'll deal with this. So, as we have these hydrocarbons, okay, how do they get used? How do we actually use them in our systems, okay? So again, solid, liquid, gas. We have all forms. Solid is coal when we're looking at carbon, or hydrocarbon. Liquid is petroleum. Gas form is natural gas. Okay, so there's 3 different states for our fossil fuels here. When we're looking at coal, it's a large aromatic hydrocarbon. So we know when it says it's an aromatic hydrocarbon that it has to have 2 or more bonds, right? So is this saturated or unsaturated? Unsaturated, right? Because if it has 2 or more, it has to be in that unsaturated category, okay? And if it's aromatic, what shape does it have to be?
Circular.
Circular, okay? So we've already been able to learn, hey, I didn't even write the other stuff about it, but I've got extra information that I know just from the name that it has, right? So coal has a whole lot more carbon than hydrogen atoms in it. So as it is burned up, as you break those bonds and you use up that energy, you've got carbon left over, which creates soot. So does that make sense now why soot looks like you colored with a pencil on everything, right? So soot is coming off as that carbon. Carbon is black. That's why our graphite pencils are black in it, and it produces a lot of soot. When we look at petroleum, typically with petroleum, you cannot use it as is. It has to be separated into a smaller form, and so it's either separated into gas or into kerosene. And then when we look at natural gas, it comes in lots of different forms because it just depends on how big the molecule is. So if we have 1 carbon, it's called methane. So it's going to look like 1 carbon with 4 hydrogens around it. When we have 2 carbons, it's ethane. Okay, so we're going to end up with 6 hydrogens around it. So this is 4 hydrogens, 6 hydrogens. Propane has 3 carbons. How many hydrogens do you think it has? Do we see a pattern? 8. Excellent. Butane has 4 carbons. How many hydrogens would it have? 10. Excellent. Okay. These are typically single chain, so they're straight in order, which means that they are also saturated or unsaturated. They all end in ane.
Saturated.
They're saturated. Okay, they all have single bonds. They end in ane. That means they have to be a saturated. So, are you seeing how we can tie? Because they talked about it as all different things. How we tie the ending into how many bonds it has, into whether it's saturated or unsaturated. We can tell all the parts of it. Okay. So right here we have 4 carbons. So automatically we can say this is butane because it has 4 carbons. It means it has 10 hydrogens set around it. Right, so I could say this has the structure of C4H10. Let's look at this one. Is it straight chain, branch chain, or circular?
Branch.
Branch chain. It has an extra little arm. How many carbons do we have?
4.
4. We have 4 carbons. How many hydrogens do we have? Can you count them?
10.
We still have 10. Okay. These have the exact same chemical structure, but they do not look the same, which means that they will not react the same. Correct? Okay. These are called isomers. When you have something that on paper looks exactly the same, but in practice looks different, we have an isomer there, right? So another thing that you talked about was complete and incomplete combustion. Okay? And I know there's a couple of you that loathe the math balancing equation parts, so bear with me here. For that, if we have C3H8, what do we have right here? If it's 3 carbons, what do we know that it is?
Propane.
Propane. Okay. So we've got propane. You've got anyone have a propane stove? Like for camping? Go camping, have a propane, typically propane stove. Okay. And we're going to combine it with air, right? So we have our oxygen in the air. It produces carbon dioxide. Okay. So we have dioxide because we have 2 oxygens and water. What type of reaction is this? Combustion. Because it produces water. And what does propane produce? Heat. Joules. Right? So you're lighting this gas on fire when there's air present. It is combusting. You're producing water. You know it's a combustion reaction, which means it also had to produce heat. Right? So when we balance this equation and we have as much as oxygen as we wanted to, we were able to produce carbon dioxide and water. Water is not dangerous. Water is necessary. Is carbon dioxide dangerous?
Yes.
Okay, are there things that it's dangerous in too small of a space, right? But is there stuff that can use carbon dioxide? Okay, carbon dioxide is necessary for cellular respiration and photosynthesis for plants and our systems to work. So it talked about all that. So we want to have carbon dioxide produced because if you have plants around or if you're outside and there's trees, okay, then it can be used up and broken down, made into glucose, and then produced back around and released back out as oxygen, okay? Now, what if we had the same formula down here and now I have twice as much butane, okay? But I have just the same amount of oxygen. All I have is 5, so I'm knowing up here. But if I double my amount of butane, what do I end up with on this side? Okay, well I would need to think that I would need to double everything, right? So if I double my amount of water, which would be 8 waters, right? Can we balance this? So I doubled my butane, which means I doubled my water, but I have the same amount of oxygen. Well, I have 2 times 8, I've got 16 hydrogens. I have 16 hydrogens, okay, so we're good on hydrogens, okay. I have 6 carbons, which means I would need to make 6 carbons there. But when I added 6 carbons, how many oxygens do I now have on this side? I have 6 times 2, that gives me 14, and 8, so I now have 22 oxygens. Do I have 22 oxygens over here? No, I only had 10 oxygens. Okay, so that doesn't work out. So to get rid of those extra oxygens, I only had enough to not make carbon dioxide, but to make carbon monoxide. okay? So I couldn't, so if I had my 5 oxygens, I don't have enough to double up over here when I have my 6. I still don't even have enough quite for that. I would need a smidge more on my oxygen level. We would need, how much would we need on oxygen? 6 times 1 is 6. 8 times 1 is 8. 6 plus 8 is 6 plus 8 is 14. 14 divided by 2 is 7. But is that double? We doubled everything else. Did I double my oxygen? No. So I was still able to produce stuff. It still wasn't double this. And what we end up with is a carbon monoxide in this. And this is called incomplete combustion. I had more gas than I had oxygen to be able to use up. And so instead of doubling up my oxygen with my carbons, it just single paired my oxygen with my carbons. And now, instead of producing carbon dioxide that is beneficial for our system and necessary for our greenhouse effect and cellular respiration and photosynthesis, I now have carbon monoxide, which gets trapped up in the ozone layer and helps us like hold some radiation and stuff, but this is deadly for us to breathe in, okay? So it's important to recognize that when we've got incomplete combustion, we can end up with stuff that we didn't want on the back end because there's a shortcut somewhere. Sometimes it reminds me, if you like to watch or see any of those videos of like where people have taken shortcuts in their jobs, you know, and the outcome is disastrous for it. So it's like when we didn't have enough to do what we needed to do and we took a shortcut, we have a really dangerous outcome there, okay? So those are all the chemical parts that you need to know. Then we started moving that into biochemistry. Like I said, we're gonna look a little bit about that with our lab today. As we moved into our biochemical part, it talked about different compounds. So we had monomers and polymers. We see the word mono and poly. Mono means one. Poly always means more than one, right? So a monomer is a single compound together. So we just have one little one. A polymer is when you take multiples of that same compound and you put it together. Okay. So what are they used for? Okay. I ran out of board room, right? Okay. So our biochemical properties break down. You read about carbohydrates, proteins, lipids, and nucleic acids. Because really, what's the point of all this chemistry stuff if it doesn't help us have enough energy to go run outside? Right? That's what we're looking for. At the end of the day, we're trying to break bonds to get the energy out. Right? Because energy is neither created nor destroyed. It only changes forms or moves from one part to the next. Right? So the whole purpose is to get the energy from that apple into me so then I can have energy to move and go run and play with my friends. Because if I'm just going to be a blob sitting on the couch for the rest of my life, that's not much of a life. So that's our whole point. Where are we going? Why do we need all of this, right? So as we eat food, as we take in vitamins, which are things that we need, but our body can't produce it ourselves, so we have to find it somewhere else and use it in our system. We get the energy from carbohydrates, proteins, lipids, and nucleic acids, and they end up breaking down in our cells, and they had a great thing about photosynthesis. We talked a little bit about this last week, and cellular respiration, and how God created this amazing circular pattern where plants take in our carbon dioxide with our sunlight, right? And they've got water, so they're going to take all of that, and then they're going to make glucose and store that in their system. and then a cow is going to eat the plant, and it's gonna break down the glucose with cellular respiration, and it's going to produce the carbon dioxide that the plant needs to take back in, and it's going to produce water over here that's going to be taken back in as well, okay? So we have this, like, I need this to be able to use it, and then you make it again so then I can use it again. So we've got this self-feeding cycle that goes back and forth between photosynthesis and cellular respiration. And so photosynthesis is always going to produce our glucose and oxygen. Those will be your byproducts. And then your cellular respiration is going to produce your water vapor and your carbon dioxide. And those are going to go back and forth, and you'll need to know that for your test. Okay? Now, how does this system run? Sometimes our engine is running a little slow. Or you have a polymer, you've taken in something, and it's this really huge, giant system with all of these bonds. And it's really complicated and really hard to break apart. Okay? So our system, God has created enzymes. If anyone bakes bread, yeast is an enzyme that we use. Okay? So enzymes simply speed up that process. Okay? So if you're swinging on a swing and you're getting yourself to start swinging, you're going to have to pump your legs a lot, right? It becomes a process. What if you have a friend run up behind you and give you a shove and do like an underdog and run underneath you? Okay? You're now swinging to the level that you wanted to swing faster because you had a push and a shove. That's what enzymes do. They give our systems a push and a shove to make that reaction go faster, so that we're not waiting well around all day long, you know. And sometimes when a system waits so long, then it dies. It's kind of like pushing a car. The friction ends up overcoming the process, and we end up slowing down. Like, so we need this to go faster so that we can actually use it, because if we don't have it, then our system's going to give up, and then it's not going to use it at all on it, okay? And so as we move over to our lab, that's what we are going to explore. We're going to look at enzymes and how they work in a system, and we are going to look at vitamins. So specifically, we're addressing vitamin C. Our bodies do not make vitamin C, but our bodies need to have it, so we have to intake it through other things. And so here, we're eating it. We put it in our mouths, right? My scary face. We put it in our mouth and it goes down, and then we've got to do something with it. Somehow it's got to get from our stomach into our system to be able to be absorbed, which means we're going to have to break all of these bonds so that we can, one, use the energy from it, B, attach the different parts from that polymer to other different elements that we have, and then eliminate what we don't need for that, right? So we're gonna look at a chemical reaction. So what are we looking for? What are the things that we can know if we've got a chemical reaction going on? Color change, precipitate, or heat. Okay, we're specifically gonna be looking at color change today. So this is a chemical reaction. It is an enzyme that will speed up a process of it, and we're looking to see our vitamin C levels in a couple of different juices for that. All right, so you guys can head over to Miss Thompson, and she will explain our lab for today.